The electric field can be understood by comparing it to the gravitational field. If I have two masses, m1 and m2, that are separated by a distance r, then the magnitude of the gravitational force that each one of those two masses feels, which is an attractive force, Fg, the magnitude of that attraction is given by Newton's universal law of gravitation. So the universal gravitational constant times m1 times m2 divided by the distance between them squared. We also know that for a unit of charge placed in the gravitational field around one of those masses, that it will feel a force Fg that is equal to m times the strength of the gravitational field, g. And so we define the gravitational field as being the force experienced by a unit of mass m. And so while we typically think of the gravitational field as having units of meters per second squared, we could also think of it as having units of newtons per kilogram. The force per kilogram on an object with mass m. Similarly, if I have two charges, q1 and q2, that are separated by a distance r, then those two charges will exert an electric force on one another. And that electric force could be attractive or repulsive, but they will be equal and opposite. And we know that the magnitude of that electric force between those two charges is equal to Coulomb's constant, K, times the magnitude of the two charges, q1 times q2, divided by the distance between them squared. And similar to the gravitational force, we can define the strength of the electric field as the force exerted by the electric field on a unit of positive charge. So an electric force Fe exerted on a positive charge Q due to an electric field E. And so the electric field is defined as the electric force per unit of positive charge Q, which therefore means it will have units of newtons per Coulomb. And so you should be able to see that there are many similarities between the electric force, the electric field, and the gravitational force and the gravitational field. So let's suppose we have a positive charge, Q, and we would like to know the strength of the electric field a certain distance away from that positive charge. In order to determine this, we're going to place a positive test charge plus lowercase q at that point. And I know that because those two charges are positive, the force exerted on that test charge will point away from the other charge. And so the force on that charge points away. And similarly, the direction of that force is going to define the direction of the electric field. And so the electric field will also point in that same direction. If the electric field is defined as the force on a unit of charge Q, then we can find the magnitude of that electric force by writing the expression for Coulomb's law and dividing by the magnitude of the test charge. And so it looks something like Coulomb's constant times the magnitude of the two charges divided by the distance between them squared. And so in my picture, I should label that the distance between these two charges is r. And so in the equation, it's r squared, divided by the magnitude of the charge Q. And so the electric field at this point, E, is given by just Coulomb's constant times the magnitude of the charge itself, capital Q, divided by r squared. And so we should see first that the electric field points in the direction that a positive test charge would feel a force, and then also that the electric field does not depend on the charge of the test charge. And similarly, when we think of the gravitational field, we know that the strength of that gravitational field, let's say on Earth, does not depend on the mass of me. And so the comparison to the electric field here is I am the test charge which feels the gravitational force and therefore the strength of the gravitational field. And so we are using this test charge to find the strength of the electric field at a certain point away from this positive charge. And because the electric field is defined as the force per unit charge, that test charge does not appear in the equation for the electric field. At this point, I'd like to also remind you that whether we are dealing with the electric force or the electric field, we need to use Coulomb's constant, K. And that Coulomb's constant is defined as 1 over 4 times pi times epsilon naught, where epsilon naught is the permittivity of free space. All of that together is equal to about 9 times 10 to the 9, and the units of that are newtons times meters squared per coulomb squared. And so when K is written as 1 over 4 pi times epsilon naught is the permittivity of free space, which is equal to 8.85 times 10 to the negative 12 coulomb squared per newton per meter squared. This image below is from a simulation which shows the electric field between a positive and negative point charge. And there's a lot of information that we can get from this picture. So from the picture, all of those white lines are showing the direction of the electric field, and even the intensity of the line is showing us how strong the electric field is. And so the first thing that I notice is if I look at the line that directly connects the positive and negative charges, and if I imagine that I were to place a positive charge, let's say at this point here, then that positive charge would feel a force to the right. It would be repelled by the positive charge on the left and attracted to the negative charge on the right. It would feel a force in that direction. And we know that the electric field points in that same direction. And so that's why all of these lines, these white lines here, are pointing to the right, because those are showing the direction of the electric field. If I start to place more points in this diagram, we would be able to make sense of why all the electric field line arrows are pointing in these directions. And so if I place a point here, then the force on that test charge, this sort of green dot is a probe or a test charge that we're moving around and seeing the direction of the electric field. At that point, there would be a force of repulsion on that test charge that points away from the positive charge, and then a force of attraction that would point toward the negative charge. And the sum of those two forces would point in this direction. And so if we place another one of those green dots over here, the same sort of thing would happen. We would get, we're pretty far away from the positive charge at this point, but we would still feel a force of repulsion that points away from that positive charge that's probably getting smaller, and then we would feel a force of attraction that's a little bit stronger due to the negative charge because it's closer. And so the sum of those two forces would probably give us a force that looks something like this. And so you can imagine many different locations where we could draw in the sum of the forces due to those test charges, and what we would get is a bunch of electric field lines that look something like this. If we imagine the same thing happening down below, I could draw a point right here, and the force on that positive test charge due to the positive charge would point this way, down and to the right, and the force of attraction to the negative charge would point this way. And the sum of those two forces would give me a force that points something like that direction. And so once again, I could get an electric field line which points something like this. Okay, so I'm not drawing that very well, but you could imagine now that all across the surface of this picture, there are many electric field lines which would start at the positive charge and point toward the negative charge, and they have varying degrees of curvature in the direction, but they will all start at the positive charge and go out and end up at the negative charge. Okay. And we put those little arrows on those electric field lines to indicate their direction. And so some of them, they go off the screen and then before they wrap around. And so some of these will just kind of go like this, and then they'll eventually wrap around and come back to the negative charge like that. And you can see outside of the two charges, the electric field lines just go away from this positive charge and toward the negative charge like that. And so everywhere around the positive and negative charge, there's an electric field due to those charges. And so we have to consider both charges, the force on a test charge due to both charges, which the sum of which will tell us the direction of the electric field. And so to sort of summarize what we're talking about here and maybe even add a few things, the electric field lines show us the direction of the electric field at a given point. We also can look at the electric field lines, and the distance between the electric field lines tell us the relative strength of the electric field. And so when we get closer to the charges, the points are closer together, and as we move further away, they're further apart, and so the strength of the electric field is decreasing. The electric field lines always start at a positive charge and move towards a negative charge. The electric field lines do not cross one another, and so at no point did I draw any of those electric field lines which are crossing one another, or at least it's my attempt that I did not do that. The electric field that we just saw previously was due to both the positive and the negative charge. Each of those charges has an electric field around it, and so what we saw was the sum of those two. If we just have a positive charge in isolation, then what we have is, if we placed a test charge anywhere around that positive charge, we would find that it would feel a force that's directed away from the positive charge. And so the electric field at any point would point radially away from this positive charge. And so what I'm doing is I'm drawing in a bunch of the electric field lines. Okay, so the electric field around a positive charge are closer near the charge where the electric field is greatest, and then the electric field gets weaker as we get further away from the charge. Okay. Similarly, if I had a negative charge, we would have the opposite case. All of the electric field lines would start away from the negative charge and point toward it, like this. Because if we placed a positive charge at any point, then it would be attracted to, it would feel a force toward this negative charge. And so even though I'm drawing these pictures next to one another, please know that I'm pretending like these two are in isolation. Okay, so they're not next to one another. And so for this reason, when we only have one charge here, then we say that the lines of electric fields start on a positive charge or at infinity and end at a negative charge or at infinity. Because if I just have a positive charge, then the lines of electric field start on the positive charge and end at infinity. And if I just have a negative charge, then the electric field lines start at an infinity and end on the negative charge itself. The last thing that I would like to show is if I have two plates, let's say here's one of those plates, and then here's another one of those plates, two plates, and one of those plates has a positive charge on it. So everywhere along this plate there's a positive charge. And then on the other plate there's a negative charge. So everywhere on that plate there's a negative charge. What would the electric field look like between those two plates? From the previous slide of the simulation, we saw that between the positive and negative charge, there was an electric field which is directed in a straight line, exactly in a straight line from the positive charge to the negative charge that looked something like that. And so if we just imagine each of the pieces of this plate as having a positive and negative charge on it, then the electric field would point directly from the positive to the negative charge. And that's exactly what we find for the plates. And so if the charge on these plates is uniformly distributed, then between two plates like this, we find that the electric field is uniform. And if the electric field is uniform, then the separation, first off, those electric field lines are parallel, and then secondly, the separation between the electric field lines, which indicates the strength of the electric field, is also constant. So all of these lines are drawn equally spaced and parallel to one another to show that between those two plates I have a uniform electric field. And similar to the diagram that we saw previously, if we want, we could place a point out here, and we could show that due to the attraction to the negative charge, it would feel a force this way, and due to the repulsion of the positive charge, it would feel a force this way. And so the sum of those two forces would give me a force that is directed downwards, like that. And if we place charges in between those two, we would find that the electric field would point something like this. And so while the electric field is uniform between the two plates, on the outside we still get curved electric field lines which start at one plate and end at the other plate. And so if on the right side I drew another point, it would feel similar forces. Force of repulsion due to the positive charge and attraction due to the negative charge, which would give me a downward force. So everywhere inside the two plates, the electric field is uniform, and outside the two plates, that's not the case.